Standard elemental value follows a strict binary. Materials are typically prized for their rare, fragile aesthetics or their rugged industrial utility. Copper, silver, and gold defy this divide. They sit together in Group 11, managing to be simultaneously attractive and highly functional. Look at the detail on these ancient gold and silver coins. Early civilizations valued these coinage metals for their beauty and their ability to endure as currency and ornamentation for thousands of years. This legacy continues today, but in a different form. These same materials now serve as the infrastructure powering modern electronics and renewable energy grids, visible in the dense copper wiring of this telecom rack. To understand the modern world, we have to uncover how the same elements humans hoarded as passive treasure became the active arteries of global technology. These gold bars are remarkably stable. Group 11 metals can exist for millennia in a vol like this without rusting or degrading. Yet, despite this chemical passivity, they are the best conductors of electrical and thermal energy on the planet. Typical metals usually trade off one of these traits for the other. Highly reactive metals conduct well, while stable metals usually act as insulators. This raises a scientific question. What hidden mechanism allows a metal to resist chemical change while effortlessly facilitating the flow of raw energy? Moving down to the subatomic level, the answer lies in a shared electron configuration. Every element in Group 11 features a single, isolated electron occupying the outermost s orbital. Because this electron is loosely held, it is highly mobile. It detaches and moves easily across a lattice of atoms, which is what creates such high electrical and thermal conductivity. Immediately beneath that active outer layer is a densely packed shell of filled d orbitals. These filled inner orbitals provide immense atomic stability. They keep the metals unreactive and typically result in a stable +1 oxidation state. This atomic geometry, a fluid, active outer layer shielding an impenetrable core, is the blueprint that bridges high conductivity with durability. As we move down the Group 11 column, this blueprint scales up. Atomic size and density consistently increase with every step. Copper serves as the baseline. It dominates global infrastructure and wiring, like this vintage cloth-covered cable, because it balances cost, conductivity, and moderate stability. Moving further down to silver and gold, melting points rise and resistance to corrosion increases. Gold is the natural endpoint of this trend. It is so stable that it acts as the least reactive metal known, refusing to tarnish even under harsh conditions. At the very bottom sits rentigenum. This is a synthetic outlier, a highly unstable element with no practical applications that marks the boundary of the group. The deeper we go into the periodic table, the more pronounced these traits become, pushing the limits of physical chemistry. Back at the human scale, Group 11 operates as a cohesive chemical family, acting exactly as its subatomic structure dictates. The conductive properties of copper and silver allowed for the miniaturization of modern electronics. We see the result in the intricate layouts and precise solder points of circuit boards like this one. Simultaneously, the stability of gold and silver shaped human geography. Civilizations sought out these permanent stores of value, driving massive migrations and economic expansions, such as the gold rushes seen here. The immense cultural and economic weight we assign to these metals is an inevitable consequence of their physical properties. Whether you are using a smartphone or admiring an ancient artifact, you are witnessing the macroscopic power of a single, perfectly placed outer electron.